Hello everyone, welcome to Mechanical Engineering. Today we are going to discuss about problems on minimum potential energy, that is from FAM, finite element methods. This comes under module 1. Okay, so we'll start with the first problem. For the spring system shown in figure using the principle of minimum potential energy. So we are using principle of minimum potential energy. Determine the nodal displacements, and here we have two forces, that is F1 and F2. Okay. In question they mentioned as F1 is equal to 75 Newton and F2 is equal to 100 Newton. So in the spring system we have three springs, and here it is fixed and here it is free, F1 and F2. So two nodes, node 1, node 2. Okay. For the stiffness, K1 is equal to 50 Newton per mm, K2 is equal to 60 Newton per mm, and here K3 is equal to 70 Newton per mm. Okay. For these springs, here the displacement is delta 1, the displacement is delta 2. For this K3, the displacement is delta 3. For overall spring system, here we have two nodes. At node 1, the displacement is U1. At node 2, the displacement is U2. Okay, we'll start the problem. As we know that potential energy is defined as the sum of strain energy plus work potential. We know that total potential energy is equal to strain energy plus work potential. Okay, so strain energy can be written as SE and the work potential is WP. Okay, so first we'll calculate strain energy, then we'll calculate work potential. Okay, as here we have the spring system, the strain energy for spring can be written as half the stiffness of the spring and the displacement square. Okay, this is for spring system. Here we have total 1 2 3 springs. So for this system I will write strain energy for the system. Okay, that is K1 delta 1 square half K2 delta 2 square half K3 delta 3 square. Okay, see here, this is for spring 1, this is for spring 2, and this is for spring 3. Okay, K1 we know, K2 we know, K3 we know, but we don't know delta 1, delta 2, delta 3. So here we have U1 and U2 at node 1 and node 2. So we have to replace this delta 1, delta 2, delta 3 by this U1 and U2. Okay, first we'll write delta 1 value, delta 2 value, delta 3 value. Delta 1 can be written as, here we have the spring system. If you consider this as a fixed point, from this to this, here we have that displacement is U1. So I will write delta 1 is equal to U1. Similarly, delta 2 is equal to, here we have delta 2. Again, for delta 2 from this fixed end, the distance, the displacement here, that is U1. So again delta 2 is equal to U1. Now delta 3 from the fixed point, here we have delta 3, this much distance, here we have that spring. From here to here the total displacement is U2, and from here to here the displacement is U1. So if you want the displacement only here, so I will take that as U2 minus U1. So here I will write delta 3 is equal to U2 minus U1. Substitute delta 1, delta 2, delta 3 in this equation. Okay, now the strain energy is equal to half K1 U1 square. Instead of delta 1 I am writing U1 square half K2. Instead of delta 2 I will write U1 square half K3. Here see we have delta 3 square, and we know delta 3 value U2 minus U1. So we know that a minus b whole square is equal to a square plus b square plus 2ab. Okay, here what is a value? u2. What is b value? u1. So I will write a square plus b square plus 2ab format. So u2 square plus u1 square minus 2 into u1 u2, that is a square plus b square minus 2ab. Okay, now work potential for the system. Okay, as we know, the work potential is calculated as force into displacement. Here we have two nodes, so we'll get two work potential, the sum of 2 points. Okay, and we have to understand one more point here, that is, if the force is applying on the system, means you have to take it as positive. If the force is by the system, then you have to take it as negative. So here these two forces are by the system, so we have to take it as negative. So I will write minus, here this is F1 and the displacement is U1, F1 U1 minus F2 U2. This is for node 2. Okay, remember this. If you are applying force on the system, means positive. If your force is generated by the system, means it is negative. Okay, next we have to add these two, so that we'll get, this is indicated as total potential energy, that is strain energy plus work potential. As we have strain energy here, so I will write this here, half I will take it as common, and the remaining is k1 u1 square, k2 u1 square plus k3 in bracket u1 square u2 square minus 2 u1 u2 bracket complete, and minus f1 u1 minus f2 u2. Okay, next half, here also we have u1, here also we have u1, here also we have u1, so I will take it as common, u1 square, here remaining is k1, here remaining is k2, and here remaining is k3, and the balance is this much, plus k3 into u2 square minus k3 into 2 u1 u2 minus f1 u1 f2 u2. Okay, as we are calculating minimum potential energy, so we have to differentiate this complete equation. Okay, that is partial differentiation with respect to u1 and u2. Okay, that is dou pi by dou u1 is equal to 0 and dou pi by dou u2 is equal to 0. First we'll do this one, differentiating, we'll name it as equation number 1. Differentiate equation 1. Okay, differentiate equation 1 with respect to u1, that is dou pi by dou u1. Here we have u1, I will write this half as it is, this u1 square becomes 2u1, as we have the differentiation of x square is equal to 2x, so here it will be 2u1, and I will write this constant as it is, k1 plus k2 plus k3. Here we don't have u1 term, so it will be 0, and here we have u1 term, so I will write 2 k3 and this one u2 minus 2 k3 u2 minus here u1 f1, so it will be f1, and here we don't have that term, this will be 0. Okay, so I will shift this f1 equal to this side, f1 is equal to, we'll get u1 k1, here this 2 will cancel, u1 k1 plus u1 k2 plus u1 k3 minus u2 k3. Okay, next similarly delta pi delta u2. Now we are doing differentiation with respect to u2. Okay, here we don't have u2 terms, so it will be 0. Directly I will write this one, half 2 times of u2 k3 minus 2 times of k3 u1, and here we don't have that u2 term, it will be 0, and here this will be f2, that is equal to 0. This 2, this 2, this 2 will cancel. Now I will write f2 is equal to minus u1, this is u2 k3 and u1 k3. Okay, so this will be equation number 2 and this will be equation number 3. Now I will solve equation number 1 and 2. Just add equation 2 and 3. Here we have f1 plus here we have f2, and here we have u1 k1, u1 k2, u1 k3 minus u2 k3, and here we have minus u2 k3 minus u1 k3. See here, u1 k3 cancel, u2 k3, this is plus u2 k3, this and this will cancel, remaining is f1 plus f2, that is equal to u1 common, I will write k1 plus k2. So u1 is equal to f1 plus f2 divided by k1 plus k2. As you know, f1 value, f2 value, k1 value, k2 value, substitute in this equation. What is f1 value as from the question? f1 is equal to 75 and f2 is equal to 100, k1 is 50 and k2 is 60. So write 75 100 divided by k1 is 50 and this is 60. After solving you will get 75 plus 100 divided by 50 plus 60. I am getting 1.59. Okay, that is u1 is equal to 1.59. Now you can take any one of the equations. See here we have equation number 3, f2 is equal to what is this? u2 k3 u1 k3. So as we know, f2 is equal to how much? f2 is 100 Newton. u2 we don't know, but we know k3, that is 70, minus u1 we know, that is 1.59, and k3 is again 70. So after solving we'll get u2 is equal to 3.019 mm. Here this is also mm, and this is also mm. So finally the answer u1, displacement at point 1, u1 is equal to 1.59 mm and u2 is equal to 3.019 mm. This completes the problem. So here we started with this spring system, then we calculate, this is the formula, that is total potential energy is equal to SC plus WP for the spring system, half K delta square. Here delta indicates the displacement. Okay, so for the system we have total 3 spring systems, so K1, K2, K3, delta 1, delta 2, delta 3. So we have to replace this delta by u1, because here delta 1, that for this displacement, that is u1 for these two, and for this total distance is u2, that is u2 minus u1 will get this much. After substitution we will get equation number 1 here, then equation number 2, equation 3 after differentiating with respect to u1 and u2. Then we have to solve equation number 1, equation number 2. So that means we have to add together, we'll get u1, that is 1.59 mm, and we have to substitute this u1 value in any one of the equation. So I will take, for easier purpose, I will take this f2. Okay, after substitution we'll get u1 and u2. Thank you so much. Tomorrow again, in next video we'll discuss some more problems. Okay, thank you, bye.